sorry. So fabrication of multi-core processors much easier. It's almost like copy and paste. And then of course you have to worry about cache coherence and so on, but they're already sorted out. So you don't need to invent something new, generally speaking. And then Intel was there, AMD was there, and Sun also invented the Android processor, and it's multi-threaded. Yeah, sure.
The constant value is big frequency.
Yeah.
Which is an S1 frequency that a single processor can work on.
Okay.
So which is
right. I think the clock frequency is. I'm not sure if it's really constant. Maybe it's slowing down. Maybe not constant. Right. Okay. The problem is the more you increase the number of transistors on chip, actually the more you decrease what is called the minimum feature size. So the transistor becomes smaller. And when transistor becomes smaller, the physical characteristics of wires and resistor changes. So actually wires become thinner, and therefore their resistance becomes higher. And also, I'm not sure about the physical scaling, but you end up having relatively larger propagation delay in the signal. Right. So I think this becomes like somehow a barrier on the maximum clock speed you can get. And also, the relative area becomes very big. So in order to have one clock which is globally distributed across this area becomes very complicated. So one of the ideas actually that is used is to have like two clocks, local clock and global clock. And global is faster, sorry, is slower, and local is faster. And actually one of the very interesting ideas called globally synchronous. Globally asynchronous, locally synchronous. So yes, actually you can move the clock all over. So maybe the term here is not very, be careful, okay, the people who is talking about this one are not hardware people. So be careful. Yeah.
But the reason can hold the scaling to the maximum frequency for the chips. The reasons that we have
maximum, as I told you, it depends. If you can divide this area into small parts, then you can have very fast clocks on the small parts. But for global clocking, yes, maybe you're right. For global clocking, for every one clock. Maybe there is now this is the hardware. But again, this depends again on the characteristics of the process technology and so on. So I can't say for sure. If you are interested, look at the electronics roadmap. Search for roadmap. I think electronics. I'm not sure. I can give you a copy of like 2011 version. I think it's called electronics roadmap. It has all these challenges. Okay, so anyway, Sun followed suit, and okay. So this was from the hardware people. Now, what happened was that this change usually was called a sea change, like a big change. Right? Why? Because you break the instruction. In order now to increase the performance of your processor, you need to write explicitly parallel programs, as we always say. And usually, this is complicated. You don't just wait in the past when you buy your first computer. If you just buy a new one, it becomes 2 times faster. Another one, 2 times faster with the same software, which is great. But now this is no longer true. You have to change the software to make it faster, or design the software from day one to scale with the number of processors. And this is, of course, a different story than just the hardware doing everything for you for free. So, right, why then the software does not scale with the hardware? Because the way your software is designed is not scalable. Right? What aspect is that? If you write, of course, in serial language, okay, there's no way to increase the performance. Of course, there is some parallelizing compile and so on. They didn't show much success in general applications. And even if you write parallel software, usually locks provide some kind of coupling, as we discussed before when we talked about test and set. So, the underlying hardware supports synchronization, but as we've seen from the cache and coherence and so on, there is overhead. So actually the synchronization itself is supported by hardware, even it's not scalable. Right. So maybe in the software here, I think what was meant here was more about like software engineering methodologies, like you write serial code and so on. Usually people don't write parallel. But anyway, so basically the whole thing about parallelism usually boils down to synchronization, and you need locks. So one processor gets the lock, and the other one tries to compete with the lock, but it's have to wait until this one. So this waiting is the thing that's causing overheads. Right, so if you use locks, things are correct, but usually not scalable, because for this case, these three processors want to operate with this structure, adding something maybe to this tree or whatever. Only one can lock the whole structure and do something to it. The others have to wait. So it is correct, but we don't scale with normal processors. You have to scale work sequentially. So this is only. Right. Now there's another thing about locking. This is the general idea of locking, but usually you can have what's called fine-grained locking. So as I said, if you lock everything, then this is good, it's correct, but it's slow. So another idea is to do what's called fine-grained locking. Instead of locking the whole thing, you just lock the part that you're working on. It seems simple, but in reality it isn't. Because if you do that, if you're not careful, you can end up having deadlocks and starvation and correctness problems and so on. So it's potentially better in terms of performance, but you can end up having many big problems. So usually speaking, or generally speaking, locking does not scale because usually it's not robust, which means that if someone who has a lock and this lock, okay, he's delayed for some reason, the others has to wait. Right. You rely on certain conventions. Usually the RM programmer's head, like the flag should be 1, right? So that should be 0. So if someone else come to check the code, it will be very cryptic. Maybe if you change 1 bit, it will make a tremendous difference. Someone is waiting on this bit and so on. And usually it's, you have to worry about being conservative, assuming worst case, you have to worry about the deadlocks. There is a problem with wake-ups. If you wake up and, okay, and someone take the work from you, you have to be careful, you have to try again. What's the complication? It's not composable. Usually it's not very elegant to write. If you are maybe transferring some item from a data structure to another data structure, right? It's not true to say, lock this one, take the value, and then insert to the other one. No, you have to lock the second first, and then lock the first, take the item, put it there, unlock the first, unlock the second. So it's not like do that and then do that. No, it becomes, you know. And there's some examples about that. So here, for instance, this one has got the lock. It looks like a cockroach here, so sorry. So anyway, this one dies or delayed, so the other one has to wait. Can't make any progress. The other thing is you have to, there's some conventions usually in the programmer's mind. This is actually code taken from Linux kernel. You can read, it's very cryptic. When a locked buffer is visible to the I/O layer, this variable is set. This means before unlocking, you must clear this variable on alpha and then clear this lock, so no reader can see. It's very cryptic code. Yeah? You have to do that, and you have to be careful, and there is a risk, and there can be deadlock. Just changing one variable. So it's not very intuitive. Maybe it's nice to get something like that for you in the exam, to have some fun, but in reality, This is not, you know, it's not good. And okay, this is some example here about complicated hard software, like a double-ended queue. So I have a queue here that can in-queue and de-queue from every end. And if you want to implement that, this becomes very complicated. If there is no interference, it's easy. But if the queue is short, it becomes very complicated to handle the locks. So you can try it anyway if you have time. Right, so if you use one lock, it's not very good in scalability. If you lock on every side, you have to worry about deadlocks and so on. So yeah, anyway. So actually, this problem was published, like one solution was published by these people in 1996. So actually, it's kind of okay. So if you just take it looks simple, like, okay, general problem, I want to insert from both sides of a queue, then you need to make a research project and publish a paper to see how to do it. So it's not something a programmer will do in half an hour in his computer. So yeah, so complexity is very high. And of course, as maybe we talked before quickly on pthreads, it's a shared memory. Usually waking up is lost. Let's see here, meaning waiting, yeah, okay, if you're waiting on something, you don't know when to wake up. Okay, so basically if someone is waking, sleeping, the other want to wake him up, he calls okay, he calls a pthread conditional signal to broadcast. Okay, so if you call this one accidentally and the current thread does not hold a mutex or a lock, then this can be like you say, I want to wake someone up and it's not me to call, right? So maybe it's bug. If you forgot that this thread is not the one who should call the signal. So if you just by mistake used to call this function by the wrong thread, you lost, and the other thread will sleep forever. Anyway, and actually this is the composition. It's not composable. So if you have like a data structure like a hash table, you want to add the item to the hash table, what you do is you lock it and then add the item, which is nice. But now, if you want to add two items, or move one item from data structure T1 to T2, in theory you can just say, okay, I'll just lock the first, delete the item, and then lock the second and insert the item. And this is not true. Because in doing that, someone else can insert an item there. So what you need to do is first lock T2, and then lock T1, and then transfer the items. Right, and then unlock. So anyway, so all these are examples about the complications you can get. You have to wait until something comes in. So, yeah, okay, let's see this one. So here, okay. Right, so here someone wants to consume an item from a queue. So this thread is waiting because it's empty. So he's waiting on the condition that it is full, or it's not empty. So if someone puts something there, it wakes up. Right. And it takes the value. Now, this does not compose. Okay, what if we want to get from either one of two queues? So this becomes complicated, how to program that. So you want to say, I'm waiting on either this one or the other one. So what you do is you have to check the first, and then to check the first and the second. But you can't just sleep on either. So anyway, so that's where the transactional memories becomes educated. Okay. Actually, our aim maybe in this talk is to get you the main idea of transaction memory. actually in these slides, the authors go more deep and actually develop or at least discuss one complete system in Java. Yeah, I mean, I don't think it is our aim here to get into that deep, but of course, if you are interested, you can find the book and we can discuss. But lots of like implementation details, and I don't think we worry about them, because usually, if you learn something too specific, usually after a time things change. But usually fundamentals stay in order. So I like to emphasize like more fundamentals and more like how to say mature concepts rather than things that are developing. And of course you can do this exercise. Right, so as I said in the start of the talk, transactions usually, not usually, but they are. They have to be atomic. And they have actually, you can say two states or maybe two operations, two main control operations. Commit, which is like everything in the transaction will appear now. Abort, nothing will appear. So it's like you're rolling back. And this very much is coupled with the idea of linearizability, which we talked about before. So basically, the whole transaction, when you make commit, it appears as if, when you make commit, as if it's happened now. So you can argue that a commit is a linearization point. So if you now look at this doubly ended queue, which was like a homework author, what you need to do is just very much similar to the sequential code. So this code is responsible for enqueuing an item X from the left side of the queue. That's what you do. You create a new node, and the left pointer of this node would point to the main entry, which is this is the object which represents the main queue structure, and then this dot left dot right should point to the new entry which you have created, and then you make the new one at the end. So it's like that. So basically you have this, and this would point to is this left, so it points to this one. This one is not like that. So if you want to insert X, you create a new node with X here, and this node is called Q. So Q equals this one. So what you do is you say Q dot left equals this dot left. So you want to make sure this one points to and then this dot left dot right. Sorry. Left and right. I just shifted them to. Right. So let's see. The node is like that. So maybe this is left. This is right. Okay, so here what you do is you say Q dot left. So this one left here goes there. And then Q dot left dot right. Check this one. Q dot left dot right. So this one points to Q. Right. And then this was left points to Q. No, actually, okay. So, okay. I just shifted them. So actually, okay, let's do it again. Rotation and will be right. Okay, so body. So it's not that. So you put it right. So you put it from here. Okay. Right. So it's like that. Okay. So this is left. And this is right. Now we want to include something from here. This is left in Q. I don't know, it seems to be working like that. So you come here, you place your Q node like that, which is the Q node, that is X. And then you see the Q dot left points to this one. And then this left implied, which is this one, points to that one. And then the main pointer will point to that one. So for some reason this code left. So it's just a standard way to, like, it's called Arabic تخيل, like thread something into the list. So this is the sequential code. So what you do in transaction, you just put the atomic. Right. So if you do that, then this is nice. So this is like, you say like, I want all this code to execute as if it's atomic, or it fails. So this is much easier if you if you try the other exercise by hand, you find this one is much easier. Okay. So let's have the break now for just 5 minutes to transfer the file.